Hi Year 12, this is our second lesson for the topic of proof. In this lesson we're going to look at direct proof. The last lesson we covered logic and the language and notation of proof. And we finished by talking about Charles Dodgson, and I gave you one of his classic logic puzzles to think about. And it was, babies are illogical, nobody is despised who can manage a crocodile, illogical persons are despised. Conclusion? Babies can't manage crocodiles. I hope you got it right. Okay, this lesson we're going to look at the process of proof, existence proof, disproof by counterexample, and then direct proof. And there are a couple of types of direct proof we're going to look at: deduction, equivalence, and proof by exhaustion. Okay, here's a cartoon to begin with. You can see here we've got some maths written here, and then we've got then a miracle occurs, and some more maths here. And the caption says, I think you should be more explicit here in step 2. And it's actually a really good cartoon because this often happens. Students get muddled up in the middle and then they fudge their way through. But a good marker will notice that and will deduct marks. Now, learning how to construct proofs takes practice. And the biggest challenge is understanding the problem. And it can help if you set out what you know, the data, and what you're required to prove. And you'll see me use this a lot, required to prove. So suppose we want to prove that the diagonals of a rectangle are equal. We can use anything that we know about a rectangle except that the diagonals of a rectangle are equal. So we could use that rectangles have 2 pairs of equal parallel sides, or 4 right angles, or the diagonals of a rectangle bisect one another. And here's our required to prove. The diagonals are equal to one another. An existence proof requires only one example to prove it. So we might want to prove that there exists a prime number n, such that n plus 4 and n plus 6 are both prime numbers. We need only one example, and n equals 7 will work because 7 plus 4 is 11, which is prime, and 7 plus 6 is 13, which is also prime. Here's another existence proof, but it's a little bit harder. Prove that between 2 rational numbers there is an irrational number. So we're going to start off by defining 2 rational numbers. I'm going to say that A is less than B. And then I'm going to also define the difference, D. So D is equal to B minus A. So suppose that A is equal to 4 and B is equal to 6. Then 6 take away 4 is 2, is the difference. Now we know that the square root of 2 divided by 2 lies between 0 and 1. The square root of 2 is 1.41, etc., etc. It's irrational. Divided by 2 is 0.707, etc. Definitely lies between 0 and 1. And this is the part where we're just thinking of an irrational number. We only need one example. Now here's the tricky bit. Therefore we can find a number z, which is equal to a, that's the smaller number, plus root 2 on 2 lots of the difference between those two numbers. Now think about it. We said that a was 4, for example. This is 0.7. and D was 2. This is going to take us part way up to B, which was 6, but not quite there. So this number definitely lies in between A and B. So therefore, between 2 rational numbers, there is an irrational number. One method of disproving a statement is to find a counterexample. And we covered this briefly in the last video. Here's an example. The sum of 2 numbers is always greater than the largest number. Can you think of an example where that statement is not true? Well, you might have said if one of the numbers is 0, then the sum of the 2 numbers is equal to the largest number, not greater than. Or you might have said if one of the numbers is negative. But we just need to find one counterexample to disprove the statement, so therefore the statement is disproven. Here's another example. Consider the following statement. If A is greater than B for all A and B that are real numbers, and A and B are not equal to 0, then A squared is greater than B squared. Either prove the statement is true or find a counterexample to disprove it. Now the key to this sort of question is to have a look at the definition of your variables. So A and B are real numbers, but they can't be equal to 0. But they can be anything else. They can be positive, negative, irrational, rational, fractions. So can you think of a type of number where A is greater than B, but where A squared is not greater than B squared? Well, negative numbers. If A and B are both negative, the statement is actually false. Let's look at an example. If A is -1, B is -2, and that fits, A is greater than B. When I square these two, I get 1 is greater than 4, which is not true. So the statement is disproven. Now there are two broad categories of proof. There's direct proof, which includes deduction, exhaustion, and induction. And there's indirect proof, which we're going to look at in the next video, which includes contradiction and proof by contrapositive. Now, probably the most familiar form of deductive proof is geometric proof. And whilst geometry is not part of the Advanced Extension 1 and Extension 2 syllabus anymore, it is presumed knowledge, so you should understand this proof. We looked at it before. Prove that the diagonals of a rectangle are equal. We had some data. Rectangles have 2 pairs of equal parallel sides and 4 right angles, and it can really help with these to draw a diagram. So what we actually want to do here is prove that BD is equal to AC, and I'm going to make that my required to prove statement. Now to do it, I'm going to do congruent triangles. So I want to prove this triangle here is congruent to this one here. So what have we got? AB is common to both triangles. We know that AD and BC are equal because they're opposite sides in a rectangle. And we also know that these angles are 90 degrees because they're angles in a rectangle. Therefore, triangle DAB is congruent to triangle CBA, reason, SAS. Therefore, AC is equal to BD because corresponding sides in congruent triangles are equal. Therefore, the diagonals of a rectangle are equal. Now, another type of direct proof is proving identities or rules like the sine rule. And here's an identity from Pascal's triangle. We want to prove that NCR plus NCR plus 1 is equal to N plus 1 CR plus 1. So we start with the left-hand side. Now NCR, that's the same as N factorial over R factorial multiplied by N minus R factorial. And NCR plus 1 is N factorial over R plus 1 factorial multiplied by N take away R plus 1 in brackets factorial. I've just expanded that part out. All right, what we need is a common denominator. So let's look at each of these terms. So we've got this one here, R factorial and R plus 1 factorial. This one's bigger. This is R plus 1 multiplied by R factorial. So I'm going to turn this into an R plus 1 factorial. And I'm going to do that by just multiplying top and bottom by R plus 1. So multiply this by R plus 1 and adjust it up here. Now I'm going to look at the other term. And we've got N minus R factorial and N minus R minus 1 factorial. This one's bigger. We want to turn this into an N minus R factorial. Again, just going to multiply top and bottom, and in this case by N minus R. Like that. Okay, collecting it all together we get this, and the numerator you can see here from N factorial R plus 1 plus N factorial N minus R. All right, factorising this N factorial out, we get this. And I can tidy this up by cancelling those R's. And I get N factorial multiplied by N plus 1, which is N plus 1 factorial. Now I've just changed this term around to be N plus 1 take away in brackets R plus 1. You can see that that's the same thing. And the reason that I've done that is because I want to get here. And this is N plus 1 factorial over R plus 1 factorial multiplied by N plus 1 take away R plus 1 in brackets. So it is equal to the right-hand side. Now, in proof by deduction, we are only proving one direction. If A, then B. But if we want to prove an equivalence, then we need to prove both directions. If A, then B, and the converse, if B, then A. Here's an example. A 3-digit number is divisible by 3 if and only if the sum of its digits is divisible by 3. So let's start by proving if A, then B. If the 3-digit number is divisible by 3, then the sum of its digits is also divisible by 3. So we're going to start with a 3-digit number, 100A plus 10B plus C. Now, why do you think I've written it like that? Because A, B, and C are the digits, and by multiplying them by 10 and 100 respectively, and 1, I've managed to write them in a place value or expanded notation format. So here's my 3-digit number. If it's divisible by 3, then that expression is equal to 3m, where m is an integer. Now we want to know what A plus B plus C is equal to. And all I'm going to do is substitute, instead of C, I'm going to substitute in 3m, take 100a, take 10b, like that. Tidying it up, I can see that that is divisible by 3. Now let's prove the converse. If the sum of the digits of a 3-digit number is divisible by 3, then the number is divisible by 3. Now you'll find with these proofs that they're almost identical forwards and backwards. You've just got to reverse it. So this time we're going to start with a plus b plus c is equal to 3m, and m is an integer. And now we want to see whether 100a plus 10b plus c is divisible by 3. And again, I'm going to replace the c with 3m, take a, take b. Tidying it up, it is indeed divisible by 3. Therefore, a 3-digit number is divisible by 3 if and only if the sum of its digits is divisible by 3. Here's another example. Prove that the lines ax plus by plus c equals 0 and dx plus ey plus f equals 0 are parallel if and only if ae take away bd equals 0. So let's start by proving if the lines are parallel, then AE take away BD is equal to 0. What we're going to do is take both of our lines and turn them into gradient intercept form. So making y the subject, we end up with y is equal to negative a on bx take away c on b. And with the other line, making y the subject, we end up with y is equal to negative d on ex take away f on e. And so the gradients are negative a on b and negative d on e. And if they're going to be parallel, those two gradients have to be equal. And just rearranging this, we get negative ae is equal to negative db, and therefore ae take away bd is equal to 0. Now let's prove the converse. If ae take away bd is equal to 0, then the lines are parallel. So starting with ae take away bd equals 0, and making a the subject, a is equal to bd divided by e. Now remember, we have equation 1 written in this form. And if I substitute, instead of a, the bd on e, I get this. And cancelling out those b's, the gradient is negative d on e. But remember, the other line also had a gradient of negative d on e. And so, since the gradients are the same, they are parallel. Therefore, the lines ax plus by plus c equals 0 and dx plus ey plus f equals 0 are parallel if and only if ae take away bd is equal to 0. And proof by exhaustion, which is also called proof by cases, requires the prover to divide the problem up into a finite number of cases and prove each one. And providing there are only a few cases, it shouldn't be too arduous. Here's our first example. Prove that n cubed take away n is divisible by 3 for all integers n. Now we're going to divide this into 3 cases, where n is divisible by 3, where it has a remainder of 1 after it's been divided by 3, and where it has a remainder of 2. And they're the only possibilities when we divide by 3. So case 1, let n equal 3k, so it's divisible by 3. K is an integer. Let's substitute that in here. So 3k all cubed, take away 3k is 27k cubed, take 3k, and this is divisible by 3. Case 2. Here we have n, when it's divided by 3, has a remainder of 1, and k is an integer. Let's substitute this in. Gives us 3k plus 1 all cubed, take away 3k, take away 1, and I've expanded that out. When we tidy it up, it is divisible by 3. And the final case, now when we're dividing by 3, we have a remainder of 2. So n is equal to 3k plus 2. Substitute it in, expand it out, tidy it up, it is divisible by 3. Therefore, we have proven that n cubed take away n is divisible by 3 for all 3 cases, then it is divisible by 3 for all n. And here's example 2. Prove that every square number has a remainder of 0 or 1 when divided by 4. Start by defining an integer n, and we're going to consider 2 cases, that n is even and n is odd. So let's start with n being even. Therefore, we can write it as 2m, where m is an integer. We want a square number, so let's square it. N squared is 4m squared, and that has a remainder of 0 when it is divided by 4. Case 2. If n is odd, then we can write n as 2m plus 1, and m is an integer. Let's square it. We're going to get 4m squared plus 4m plus 1, and that has a remainder of 1 when we divide by 4. So therefore we've proved it. For all n that are integers, n squared will have a remainder of 0 or 1 when divided by 4. And that's it. In our next lesson we're going to look at indirect proof.